In just a minute, it will be my absolute pleasure to roll out this week's seminar with Aashish Clerk. I'm so glad you've joined us on time. Before we begin with introductions, we love to give everyone just about a minute or two to tune into the live stream. And that's a good time to begin to practice how to ask questions, interact, and discuss during the seminar. You can type in the comment chat box on YouTube where are you tuning in from today. Myself, Quebec, Canada. You can find that comment chat box on your YouTube window, somewhere above, below, left, or right. I'm sure you can find it. Feel free to type in there. There's a little bit of a delay between when you type things and when we see them. But that's the same place where you can ask questions of live of Ash and myself during the talk, as well as the place where you can answer and discuss as we go along. We like to keep this very lively and interactive. Now, you can go back and rewatch the talk, and this seminar takes place every Friday at noon Eastern Time, and will be hosted on this YouTube channel. So to stay up to date, you know how to subscribe. You can always go back and rewatch things, but you can only discuss live with us Friday at noon. And I think with that, folks, I'd like to give Ash as much time as we can. So let's just get right into it. I'm thrilled to roll out the latest episode of the IBM Qiskit Live Quantum Seminar series dedicated to you, the academic and research quantum communities. I'm your host, Zlatko Minev from IBM Quantum Research. And today I have the special pleasure and privilege of hosting Aashish Clerk from the University of Chicago, the Pritzker School of Engineering. Ash received his bachelor from the University of Toronto and a PhD in physics from Cornell University. Prior to joining Pritzker, Ash served as professor of physics and was at McGill University in a tier 1 position. Ash's work has been recognized by many awards, including the 2020 Simon Foundation in Physics Fellowship, the 2015 Rutherford Medal in Physics, and from the Royal Society of Canada. With that, Ash, it's a real pleasure to welcome you here. How are you today?
I'm good. Thank you, Zlatko, both for the nice introduction and the invitation to speak here. This is, looking forward to it,
Yeah, likewise. Just tell us where you're tuning in from before we let you take it away.
I'm in Chicago, Illinois. Actually, not on campus. I'm at home, so it's the South Loop for people who know Chicago. So just right by the lake, a little bit south of Grant Park.
Yeah, I'm glad we could connect here virtually. I was in Chicago 2 days ago.
And I used to live in Quebec for many years, right? So in Montreal. So yeah, there's.
So we've made this possible. Folks, feel free to ask questions as Ash goes through his talk. And Ash, the stage is yours.
Perfect. So if we could start the slide sharing, that would be great. And that looks like it's working. Perfect. So again, thank you, Zlatko, again for the invitation to speak, and also for all the work in putting together this series. I think it's a great service to the entire community. So the title of the talk that I'm going to give you today, Correlated Quantum Noise, Surprises and Opportunities. I'm going to tell you about some recent work in my group on a topic that I think is kind of fun for a number of different reasons. So on the one hand, this topic of correlated noise is definitely relevant to sort of quantum information and quantum technology. But it's also fun because it actually touches on a number of kind of fundamental sort of issues in quantum physics. So time permitting, I hope to tell you about two stories, two sort of recent pieces of work coming out of my group. So the first is a kind of theoretical study of spatially correlated quantum noise, and kind of the simplest possible, seemingly boring setting, spatially correlated dephasing noise. I'm going to try to convince you there's surprises there, that this spatially correlated dephasing noise can be surprisingly quantum. Sometimes it can actually create entanglement. And there's also connections to, again, some surprising kind of pieces of fundamental physics. So connections to time reversal symmetry and how time reversal symmetry is related to the ability to create entanglement. So that's the first story I want to tell you about. Time permitting, the second story now turns not to correlations of noise in space, but correlations in time, so non-Markovian noise. I want to tell you about some recent work where we're pretty excited about it. It's a kind of simple way of modeling driven qubits that are driven by classical non-Markovian noise. And by simple methods, it's almost as simple as using the Lindblad master equation. So that makes simulations really nice. It's also a method that we think gives you a lot of physical intuition as to what's going on. So that's the plan. Hopefully get through a big chunk of that. Let me start by acknowledging, of course, the people who really did the work. So this first story about spatially correlated dephasing, the main players are a PhD student in my group, Yuxin Wang, and Alireza Saif, a former postdoc in my group who is now at IBM. And then the second story I'll tell you about, this non-Markovian noise modeling, that also involves Alireza. It was led by, again, a former postdoc in my group who just recently moved to Oak Ridge, Peter Grozowski. And it was also in collaboration with Professor Jens Koch at Northwestern University. Okay, so let's start with a sort of a big picture, sort of a motivation for the sort of ideas I'm going to tell you about. Here's a cartoon that sort of describes in a very simple way something I think a lot of us worry about. We have some nice, pristine quantum system. We want to control its unitary evolution to do beautiful things. It's coupled to all sorts of degrees of freedom, the environment, a bath, that tend to corrupt all the nice stuff we want to do. So for a superconducting circuit, this might be other electromagnetic modes in the circuit. It might be quasi-particles. It might be phonons in the substrate. And so what we're often interested in doing is to mitigate the effects of this dissipation. We want to come up with some sort of effective description, right? We don't want to keep track of everything going on in the bath. We want some effective description, for example, a master equation telling me about the evolution of the system degrees of freedom. And we also want a way of thinking about the terms on the right-hand side here. And often the way we want to think about that is almost the way we think about dissipation classically. We'd like to think about it in terms of noise. So noise is being injected from the bath into the system. And also in terms of dissipation, right? Energy in some sense can leak out of the system into the bath. Okay, so understanding this, of course, is important if we want to actually have any hope of being able to mitigate the bad effects of this bath. But this sort of noise and dissipation in the quantum realm is in itself of sort of fundamental interest, right? So right away, even if we're starting with a practical motivation, we're led to some kind of interesting basic questions. So how is quantum noise distinct from classical noise? When I have this interplay of dissipation and driving of the system, how do I describe that? What comes out of that interplay? And also, is it possible to use noise and dissipation as a resource itself, right? To actually get useful evolution. Okay, so that's the general setting for the work I want to tell you about. I think something I often face when I tell students who are thinking about working with me that, look, this is the kind of thing we look at, people get depressed. It seems like, wow, there's all this beautiful stuff at the level of the system, and you study how it goes away, right? When you add all this sort of, dirt, right? The noise and the dissipation. And I want to maybe remind you that that's not the case. There's a lot of beautiful physics and phenomena that only really comes to light when you study fluctuations, when you study dissipation. So really quickly, here are two kind of favorite examples in that sort of venue. So here is a really beautiful talk and paper, right, from Einstein in 1909, where people were still worrying about what is the photon? How should we think about light? Is it a particle? Is it a wave? So Einstein analyzed this kind of Gedanken experiment that's sketched here. You have a harmonically suspended mirror. It can move back and forth. It's in a cavity that's filled with thermal radiation, right, thermal light. It had been known since the time of Maxwell that, look, there's radiation pressure. The photons can kick around, right, this mirror. And so what Einstein did is said, well, let's look at the motion of the mirror. Let's look at the fluctuations in that radiation pressure force. And let's try to use the Planck formula to understand what is the statistics of this noisy force. And in a really beautiful calculation, he shows that the statistics of this noisy force has both a term that we'd associate with particles just bouncing off that mirror. It also has a term that we'd associate with random waves. So a really beautiful sort of early example where studying fluctuations, quantum noise, reveals something about wave-particle duality, right? Kind of a more recent example, a very different looking system. So this is supposed to be, again, the world's simplest electronic conductor, a tunnel junction where I put a voltage across it. I have electrons tunneling through this barrier. Some are transmitted, some are reflected. If you look at the fluctuations in the current through this barrier, right, this shot noise, right, you find that the fluctuations in current
are proportional to the average current. And the prefactor there actually tells you about the charge of the carriers. Right? So one kind of amazing and subtle thing you can do is, if you now have some kind of strongly correlated electron system where the quasi-particles carrying the charge are not electrons, but fractionally charged objects, studying the fluctuations of current gives you a way of actually accessing that. Okay, so the big message here is noise is not just some nasty thing that corrupts the nice physics we're after. Noise and fluctuations in the quantum realm are actually an interesting way of learning new things about quantum physics. Okay, and there's going to be an aspect of that in the two stories I want to tell you about. And again, the two stories I want to tell you about, one has to do with spatially correlated dephasing noise and surprising quantum features, and that's the first thing I'm going to tell you about. And then towards the end of the talk, I'll get to the second story, which has to do with non-Markovian noise. How do we model that when we're also driving our qubits? Cool, so let's launch into this first topic. And the first topic is correlated noise. And again, just to motivate, again, the idea is that we have a bunch of qubits coupled to some common noise source or common bath. The fluctuations they each see are not independent from one another. So coming from a kind of practical motivation, this is something we know we have to worry about for quantum information processing. It's well known that if errors in noise are too correlated amongst our qubits in some processor, that's a challenge for quantum error correction. So here are even some relatively early papers that discuss how this is a limitation for the surface code. We know from recent experiments in superconducting circuits that there is strong evidence for correlated noise, right? So these beautiful experiments from Robert McDermott's group, from the Google group, seeing correlated charge fluctuations, right, amongst different superconducting qubits, seeing correlated drops, right, in the T1 relaxation times of the qubits. So some level of this correlation physics is really at play in the systems we care about. There's also the aspect that maybe if we have noise correlations, maybe that's actually a resource. Maybe we could do something with that. Okay, and this is something I'm not going to really discuss, but there's this beautiful idea of spectator qubits. So if we just zoom in here, this is supposed to be a collection of qubits. The idea is if they're all seeing the same fluctuations, maybe I can use one of them as a sensor. It can be used to detect that correlated noise, and we could use that information to cancel, to some extent, the noise on the other qubits. Okay, so there are lots of motivations for thinking about correlated noise coming from quantum information. The story I'm going to tell you about is really not focusing on any of these particular things. It's really trying to ask some very basic questions about correlations of noise in the quantum realm.
And Ash, quick question to clarify, since there was a little bit of discussion in the chat about correlated classical versus correlated quantum noise and what that means in terms of maybe operators of the coupling, or how you make sure you differentiate between the two.
Yeah, and that's a great question, and it's a question that has many, many answers. A big bulk of the things I'm going to tell you about over the next 10 minutes is a particular way to sort of answer that question. Right, so it's a great so the answer is, or at least one way of answering it, is coming in just sort of 3 minutes. And it's a really good question. What exactly do we mean by that, right? And there are different ways you could choose to distinguish these two things. I'm going to try to convince you that there's a particular nice way of drawing that cut that's powerful, right? And so, great question. We're coming right to it. Is that good, Zlatko? Yeah. Okay, so let's start the stage. I'm going to talk about, again, what might seem like a very, very simple problem. We're just going to focus on dephasing noise. And to begin with, we're going to really think about the dephasing noise as being just completely white noise. So let's just think about classical noise, one qubit to begin with, just to set the stage properly. So I have a single qubit. It's coupled to some classical noise source. This is my Xi of t. That's the noise. This Z is the Pauli Z for my single qubit. So this noise is causing the splitting frequency of the qubit to fluctuate. The noise is white. So if I look at this correlation function, no correlations at different times. There's just one number that parameterizes the strength of the noise. So the qubit splitting frequency is sort of fluctuating. That means that if I have a superposition, right, the phase of that superposition is going to pick up some random value. So I could look at that in terms of this off-diagonal density matrix element So 1 and 0 are the computational states. They're Z eigenstates in the notation I'm using. So if I average this phase over the statistics of this noise, right? And let's just even take it to be Gaussian. I'm going to get dephasing. I'm going to find that coherence basically decays with time, right? So this is like the standard simple picture of dephasing due to white Gaussian classical noise. So this sort of dephasing dynamics we can also describe with a Lindblad-style master equation. So this rho now is describing the density matrix of my qubit averaged over different realizations of the noise. And this dynamics here, right, and this is our Lindblad superoperator. Z again is the Pauli Z for my qubit. This is exactly describing this tendency for the off-diagonal density matrix to decay exponentially. Okay, and again, this is so we can get this starting from classical noise. We could also get this from a model where we started with a quantum bath. So this is the interaction of my single qubit with the bath. Here is some funny bath operator, right? Maybe it's a sum of creation and destruction operators of bosonic modes in the bath. In the limit where that quantum bath is Markovian, let's say maybe in the high temperature limit, will be led to a similar master equation. Okay, so the starting point, just one qubit, no spatial correlations. This quantum master equation that describes dephasing is equivalent to driving with this sort of classical noise, right? Two different ways of describing the same thing. Let's make life more interesting. Let's go from 1 qubit to n qubits, okay? So now I have n qubits. They each have their own Pauli Z, and they could each be driven by their own fluctuating noise. Okay, so it's all classical noise right now, right? We're still going to take the noise to be white, right? So if I look at this autocorrelation function between the noises, delta function in time, but now the noise on, I don't know, qubit 5 and qubit 8, they could be correlated with one another. So now we have not just one number that characterizes the noise, we have this covariance matrix, right? This, if there's n qubits, this n by n real symmetric matrix that both tells me the strength of a particular noise process and how is one noise process correlated with another. Okay, so this is now like many qubits, many white noise sort of processes that might be correlated. Again, we could turn the dephasing that's generated by this noise on our qubits into a Lindblad-style quantum master equation, right? And so now we have that same structure. And again, this is describing this correlated dephasing. The covariance matrix of the noise shows up as the coefficients in this master equation. And again, we're summing here over all pairs of these Pauli Z operators for the different qubits. Okay, so this is all still classical. This is classical correlated noise. What's a good picture of this? Well, look, this is a real symmetric matrix. If you see a real symmetric matrix, you should probably diagonalize it, right? You'll get more insights. So if we diagonalize this matrix, we'll get some eigenvalues, we'll get some eigenvectors. And that gives us even a nice picture classically, right? So this problem here is equivalent to having now a set of independent noise sources. So this is the case of just 3 qubits. And those independent noise sources are actually coupled to all of the qubits, right? So these independent noises, how do they couple to each of the qubits? That is basically determined by the eigenvectors of this matrix. And the eigenvalues sort of tell me the strength of the noise. Okay, and the same thing works if I start with this quantum master equation. I could write this in a better form, basically by using the diagonalized form of the covariance matrix. I can write it now as a sum of these Lindblad dissipators, right? Each term in this sum corresponds to one of the eigenvectors and eigenvalues. And I see that each term here corresponds to some dephasing process that involves a linear combination of the different qubit sigma z operators. And the crucial thing here is this matrix here is, these vectors here are real, right? We can imagine them showing up in this Hamiltonian here, right? They're the eigenvectors of this real symmetric matrix. Okay, so this is all classical correlated noise, right? Classical correlated noise, it can do interesting things, right? It means the dephasing rates in this system are not just additive. If I have a 2-qubit superposition, the dephasing of that superposition is not just add the dephasing rates of qubit 1 and qubit 2. This kind of noise can generate classical correlations between the qubits. Crucial thing, this noise will never generate entanglement, right? Despite the fact that there's correlation here, the noise's effect on the qubits, at best it will generate classical correlation, no entanglement. And a simple way of seeing that is if you go back to this kind of stochastic picture, every qubit is just driven by its own field, right? So for a particular realization of these noise processes, right, my evolution is just a product of unitaries on each qubit. Just averaging over that is not going to generate entanglement. Okay, so the story so far is if I come to you with a master equation like this, right, and this matrix is real and symmetric, right, it's going to be in Lindblad form, we know this is equivalent to classical noise, right? And we know it's classical correlated noise, it's classical correlated white noise. No entanglement is possible. Okay, and we might think that, okay, this is sort of like, you know, close to the world's most boring master equation for a collection of n qubits, because look, it's only z's, everything commutes. It's the same as, you know, classical noise. So let's ask an innocuous question. Let's try to make this slightly less boring. Okay, let's not do something drastic, slightly tweak it. What if I allow these coefficients here to actually be complex, right? So let's take this matrix of coefficients, this n by n matrix, and let's make it a complex Hermitian matrix, and let's make sure it's still positive, right? So now if this matrix V is complex Hermitian positive, this is still a completely valid master equation. It's a Lindblad master equation. It's a valid evolution of the density matrix, right? According to the rules of quantum mechanics, right? So this is still allowed. It's still dephasing only dynamics, right? Just by making this complex, I can't flip the state of a qubit, right? It's all z's, everything commutes. But what I'm going to try to convince you is this is no longer as boring as it might seem. The simple step of making this matrix here complex, Hermitian and positive, means that this is no longer going to be equivalent to just driving my qubits with correlated white noise and averaging. Okay, yeah, Zlatko?
Yeah, maybe before I let you go a little bit too further, quick question on connecting the context of the theory to some experimental situations. I imagine that this is a really good model for something like ion systems, where you might have, you know, several fluctuating magnets really far away, and each one has a different influence on all the ions, so you kind of have multiple sources, and that's a really good model. I imagine for superconducting qubits, where we believe most of the noise is quite local, maybe except for flux tunable devices, you know, you wouldn't really have so much spatial variation. But yeah, maybe if you help me connect it a little bit to experiment, that'd be great.
Yeah. And so I think one of the, either virtues or drawbacks of the way I'm describing things is it's meant to be very, very, very generic. It's also meant to, at this stage, be sort of agnostic to whether, do you have a lot of correlation? Do you have a little bit of correlation, right? Whether it's one of those two extremes is really the form of this V matrix. How big are the off diagonals? One interesting question, even in, for example, superconducting circuits or most platforms, we have a lot of beliefs about how correlated do we think a typical noise environment is, right? So even like if you have flux tunable superconducting circuits and you have flux noise, to what extent is there any spatial correlation there or not, right? And so you could sort of argue, well, look, I think I know what the sources are. It should be very, very local. But really, really systematic ways of probing that correlation. I think Lorenzo Viola gave a really nice talk on sort of noise spectroscopy methods. One aspect of that is even, yes, you want to understand the structure of noise, let's say in frequency space, but you'd also like to understand and even bound how strong are these correlations, right? So here, like the motivation of this work, it's even like stepping back from any particular experimental platform. It's really asking, if we think about all the different ways noise could be correlated, right? Are some of those means more classical, or some of those correlations more quantum? I think that the thing that sort of connects to this is then, in a real experimental system, you would really like to do some proof of principle experiments where you actually probe, do these correlations exist?
And towards the end of this section of the talk, I'll mention like a concrete protocol for how would I test whether these correlations exist or not.
I see. And quick question from Laxmi. I suppose all of this translates equally well to continuous variable systems where you play Z with something like A dagger A.
That's a really interesting question, and you know, it does. So the story I'm going to tell you is, even though everything commutes, life can be interesting in quantum. So you can imagine a continuous variable system where the simplest thing would be you replace these Zs by, let's call them position operators, right, or quadrature operators. So then you have a very, very similar structure, but there are some things that are actually different. So actually we're almost finished writing a paper on this. Maybe once I present some more of the results, I can tell you how things change in the continuous variable case. So it turns out, like many things, not having an infinite dimensional Hilbert space can make things even more interesting. But this idea of this V matrix, right, is it purely real? Is it complex? If it's complex, there's something more quantum there. That's also completely true if we had a continuous variable system and these were like Hermitian operators like position. Yeah.
Thank you.
Cool. Okay, so where are we? We have basically, what I'm trying to convince you is, if the V matrix describing the correlations in this dephasing process has complex entries, then this is not equivalent to sort of just having classical noise driving our system. And again, one way of seeing that is if you diagonalize this master equation, again, these are the eigenvalues and eigenvectors, right, of that V matrix. These eigenvectors are now complex, right? So I cannot just connect that to some stochastic classical Hamiltonian with some noises that couple to the different qubits, right? Because this Hamiltonian would have to be Hermitian. Okay, so this is a valid master equation. It doesn't look like classical noise. What does it actually do, right? And again, we get to some of the questions that I think people have already asked. In what sense is the resulting dynamics sort of more quantum when V has complex elements? And also physically, this is sort of getting to Zlatko's question, what physical bath would give me that? So it's all fine and well as a theorist to just write something down and say cool stuff happens, but what would you actually have to build, right, in terms of the bath that your qubit is coupling to get these complex elements? Okay, and so let me give a simple example to sort of tell you what I'm going to use as a metric for things being more quantum. So let's just consider 3 qubits, right? And an example where for these 3 qubits, this V matrix is going to have complex elements. So I'm going to have a single Lindblad dissipator where it's a linear combination of Z1, Z2, and Z3. But now I have these phase factors, right? So depending on the value of theta, I could have complex numbers here. So if theta is 0 or pi, everything is real. You expand it out, this V matrix is real. That's classical noise, right? If it's different from that, then it's not classical noise. So what's a consequence of that? The consequence of that is if I take theta different from 0 and pi, and I have this dephasing process, this master equation can generate entanglement. Okay, so that's what's shown here. If you start with a product state, so these are the plus states, so just equal superpositions of 0 and 1. So I have this product state. I evolve under this kind of purely dissipative dephasing process. I can actually generate entanglement between qubit 1 and qubit 2 plus 3. So that's my bipartition. The entanglement here is measured using the log negativity. And again, the crucial thing is this generation of entanglement, which again does die away, that would never be possible if we had just classical noise driving our qubits. And I think this will now come to my long delayed answer to one of the questions that was asked. In this setting, what's a good way of distinguishing classical versus quantum correlated dephasing? Can the correlated dephasing actually generate entanglement, right? And if it can, you're doing something that just driving with classical noise in the way I described would not be able to do. Okay, so now the kind of question is, okay, if the V is complex, there's something more quantum here, we can generate entanglement. Why is this happening? How do I understand that a little bit more physically, as opposed to, well, look, it's not classical noise, anything can happen, right? We want to have a better answer to that. Okay, and then one piece to sort of complicate the story is, you might think, oh, as soon as you have imaginary coefficients in the V matrix, you're going to get entanglement. It's not classical noise. Generically, why can't you generate entanglement? Well, it's not as simple as that. So if I take this dissipator for just 2 qubits, and again, this R is some real number. Let's take it less than 1. This is definitely a complex number with an imaginary part. This dissipator, right, will never generate entanglement. Okay? So if I have a complex V, it's possible for the dephasing to generate entanglement. But just because I have complex numbers, it doesn't guarantee I get entanglement. So things even get a little bit more complicated. We really want to understand what is the kind of entanglement generation mechanism here.
Ash, and maybe you'll get into this. Just intuitively, if I try to find a way to think about what this means, could I think of the trajectory evolution and say what happens under a collapse or a jump operator? And if I have Z1 plus some phase Z2, that's a bit like giving qubit 2 a phase kick when you have this jump, and it's a correlated jump between 1 and 2, and there's a phase kick. And if that phase kick is like a pi/2 rotation, maybe that creates some entanglement. Or
yeah, and that's a really good observation, and it's almost sort of 2 slides away. So one of the things
maybe I should hold up. I'm sorry.
Yeah, it's good. It's good. One of the things I'm going to tell you about is one way of interpreting this. Again, it's a particular kind of trajectory unraveling. Is to actually think about this as sort of describing the unconditional evolution under measurement and feedback. Okay, or a measurement and feed forward. So I can imagine if you want unraveling the master equation in a kind of diffusive way, such that it describes I'm actually measuring some qubits and then doing stuff to other qubits. And then in those situations, I can really say something about will I get entanglement or not. So literally 2 slides away, very very forward thinking of you, Zlatko. So
okay.
Great.
Thanks a lot. This is great. It probably also connects to all mid-circuit measurements and feed forward, which is a big theme these days too.
Awesome, yeah. So what's one way, we'll get to that feed forward and measurement-based way of thinking about it. What's one way of understanding what's going on in nu when this V matrix is complex? Well, the idea is that this bath, right, that's generating this dissipative dynamics, it can mediate interactions between the qubits, right? It's more than just a noise source. It's making the qubits interact. But it makes them interact in a really funny way, in a way that I'm going to call a non-Hermitian or a non-reciprocalizing interaction. Okay, so what the hell is that? So this is a Hamiltonian evolution of just 2 qubits with a standard Hermitian Ising interaction, Z1.Z2, right? What is the dynamics, right, from a Hamiltonian like that? Well, heuristically, each qubit produces a Z magnetic field on the other, right? So if I look at the X1 operator of qubit 1, right, it's going to process, right, with a sign here that depends, is qubit 2 up or down, right? And everything's symmetric. I have the same evolution for qubit 2. So what happens when I write down one of these funny dissipators, right? There is an interaction between the 2 qubits, and I put a J here kind of suggestively. Again, I've got the I over here. If I now look at the equations of motion for just the average values, right, of the 2 qubit coherences of X1, I see some dephasing effect, right? I see there's a tendency for those things to decay. But the interesting thing here is I also see some tendency to process, right? I see terms like these 2 terms over here, right? So it looks like what I would get from an Ising interaction. But what's the crazy thing that tells me this couldn't come from a Hamiltonian? Let's look at the signs. So if I really had a Hamiltonian, these signs are identical. With this dissipative Ising interaction, these signs are actually opposite. Okay? So the bath is mediating a kind of interaction between the qubits. We know interactions can generate entanglement. That's not surprising. The interaction that's at play here, you can't describe with a Hermitian Hamiltonian. Right? If you try, there's this sign problem that you have. Okay? So again, our question right now, why does the complex V matrix lead to entanglement generation? One way of refining the puzzle is we do have bath-mediated interactions. They are these funny kind of non-Hermitian Ising interactions. Okay, let's get a second picture that maybe connects more to sort of the microscopics, right? Let's actually think about the bath that's sort of generated right, this master equation. So let's imagine we coupled our qubits to some common bath with some system bath interaction Hamiltonian like this. So for each qubit, I have the Pauli-Z operator. I have some bath operator for each different qubit, these B's, they're Hermitian, right? And now you can do the standard Born-Markov type derivation of a master equation, this dephasing limit to get this. And you can relate this V matrix, right, to the properties, the correlation functions of these bath operators. And the question we want to know is, how on earth do I get these imaginary terms here? The imaginary coefficients that actually lead to the possibility of entanglement generation. Okay, so here is something that theorists love and experimentalists tend to not love that much, right? I'm going to write down a Green's function. Let's call it a susceptibility. In my experience, that doesn't frighten people as much. So there's this quantity I could calculate, and this is an average with respect to whatever the state of the bath is, right? It's this commutator of the bath operator for qubit J and qubit M. What does this tell us in words? In words, this is a susceptibility, right? So imagine I'm doing chi 1,5. It's basically telling me if I try to drive the bath through this operator B5, how does the expectation value of B1 change? Okay, so that's that susceptibility. If I flip the indices, it's the opposite question, right? If I tried to drive the bath via B1, how does B5 change? So now there's a really, really simple and beautiful answer to where did the imaginary parts of V come from? They come from an asymmetry in those two experiments I described to you, right? If I drive M and try to change the average value of Bj, or vice versa, if those two things are not the same, that's exactly where I get this imaginary coefficient in V. Okay, so this is something now you could use if you have a model of what your bath is. This is a direct way of using your microscopic knowledge to understand if you get these imaginary V's. But it also tells you something very, very physical, right? If my bath has time reversal symmetry, right? So both the state of the bath, the Hamiltonian of the bath, I also want these coupling operators B to all have a definite parity under time reversal symmetry. So if that holds, I can use an Onsager relation. This has to be 0. Okay, so now we have something that I think was a surprise to us when we first uncovered this. When do you have this more kind of quantum dephasing dynamics? When is that possible? You necessarily need to have broken time reversal symmetry. If you have time reversal symmetry, right, this V matrix has to be real. If you don't, all bets are off, right? And that's another interesting aspect of this whole story that I won't delve into more. You could almost imagine this kind of physics I'm describing here as a very funny kind of way of probing the properties of some unknown bath. It's a very sensitive way of trying to understand, does this mysterious bath have broken time reversal symmetry or not? And kind of going back to Zlatko's question about, okay, what about a realistic system, something we care about, whether it's superconducting circuits, whether it's trapped ions. We often use magnetic fields in our system. We're often out of equilibrium. We've been driving our qubits, right, doing pulses, right? Generically, you can imagine a lot of different reasons why the effective environment your qubits are seeing are not actually in a time reversal symmetric state, right? So one upshot of the content on this slide, we can say something about when these funny imaginary elements of V show up. It's when the bath has broken time reversal symmetry. Okay, and then finally to
very quick question on that. So the way, so if the bath was a pure, it was, let's say, a closed, isolated, finite number of degrees of freedom quantum system, then wouldn't have time reversal broken symmetry. It would have to have its own dissipation or be chaotic or something like that, right?
So in terms of getting the imaginary parts of V, or even to just have that be viewed as a bath?
Yeah, I guess it's a good question because, what we mean by
this nice philosophical question. When is my system a bath? So very crudely thinking, I'm thinking of the bath as something that has many, 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 many degrees of freedom, right? I'm thinking of the bath as like almost having a continuous spectrum, right? I can't really resolve discrete resonances. I'm also thinking about being in a limit where I'm coupled to the bath weakly enough, right, that I can use this kind of master equation. And so what that means is the time scale for all of the dissipation and dephasing described by this master equation, that should be much, much longer than the time scales that it takes for the bath to relax, right? So it's this kind of usual hierarchy of scales that we like to have, to think of the bath as being a good bath. There's obviously all sorts of interesting questions. When is your bath, if your bath is not a good bath, right? It doesn't relax quickly, right? And that's almost the second part of the talk if I get to it. How do we think about that? But part of the message here is even in the simplest case where we make all of the nice approximations, there's some surprises in this seemingly innocuous master equation.
I see. In a canonical bath that you would pick up in a Gardener's Zoology book or something like that, that always has time reversal symmetry, right?
It's actually not something that we, like it typically doesn't show up in the kinds of things that we sort of think about, right? So, so typically we might say that, we have a whole bunch of harmonic oscillators with some flat spectrum. They're all in their ground state, right? But then there's still a statement of like, what exactly is the time reversal operator, right? What exactly are these coupling operators, right? How does everything transform under that? So then it's typically something we just don't even have to specify, right? It's kind of irrelevant to everything that we're doing, whether is there some anti-unitary that leaves the state of the bath, right? The coupling operators invariant or changes them by a sign. And that's actually one of the surprising things here, at least. I'm not aware of too many other examples in kind of basic dissipative quantum physics where whether you want to or not, you're forced to think about time reversal symmetry. You can step back and go, okay, from a condensed matter point of view, if you write down a Hamiltonian and there are eyes in the Hamiltonian that you can't get rid of, right, by some clever gauge symmetry, well, then you have broken time reversal symmetry. So there's something similar going on at the level of this master equation. When I have this V and it has sort of complex entries, right, there is really hidden in the problem a notion of broken time reversal.
I see. Because usually I think in like the Caldera-Leggett model, I think of breaking time reversal symmetry by kind of ad hoc, almost inserting a finite time horizon, inserting a little bit of an imaginary time evolution, some plus I epsilon in those e to the I rotations. I'm just trying to understand the physical model that would lead to your bath having this time reversal symmetry. How do I go about thinking of what could physically cause that?
Oh, so you could imagine a situation where, so imagine my bath is like a collection of phonon modes, right? And imagine I've driven the bath out of equilibrium, right? So that like, look, there had been some event where, I had actually pumped the bath, maybe accidentally in a particular way. And so now I've really excited phonon modes at a particular frequency that are all moving to the left and not moving to the right, right? So that would be one way in which the state of the bath now, right? I've sort of favored the population of phonons going in one direction, not the other, right? That's sort of a broken time reversal symmetry. In general, like even just the magnetic field, right? Acting on whatever the degrees of freedom in the bath are, if they're charged, right? Formally, right? That would be enough to give you some broken time reversal symmetry.
Okay, thanks, Ash.
Cool. Okay, so third way of thinking about things that finally connects to the nice intuition that Zlatko had. Because again, we still have this question that just because the V is complex, it doesn't guarantee, right, that we have the ability to generate entanglement. So there's another nice way of thinking about master equations like this when V has complex entries. And that's this connection to continuous measurement and feed forward. So let's again take a really simple version, a 3-qubit version of this general dynamics. Let's write a single Lindblad dissipator that has an I in it. This lambda is going to be a real coefficient. And so what I can do when I have a dissipator like this is separate the qubits that enter with a real coefficient in the dissipator and separate the ones that come with the imaginary coefficient. So I've got these two groups of qubits, again, much like what Zlatko was saying. How can I now think about this dynamics? Well, it turns out this master equation is rigorously equivalent to imagine doing some measurement and feed forward process and then just averaging over all the outcomes of the measurement. So this is what this cartoon is supposed to represent, and I'll walk you through it. So qubit 1 and 2 are over here, one group. Qubit 3 is this group. So what's going on here? I have two measurement and feed forward processes. So in this direction, some person is measuring qubits 1 and 2. They have some continuous measurement record that's trying to follow what Z1 plus Z2 is doing. And then they're using that information they've gathered to drive qubit 3. Okay, so that's the feed forward, right? We're taking information from 1 plus 2, putting it into 3. But on top of that, we have the reverse process going on. Some other agent is measuring qubit 3, right, in the same way, measuring Z3, using that information to drive qubit 1 plus 2. Okay, so using these kind of the theory of continuous measurement and feed forward, averaging over all of the possible measurement outcomes, all of the noise, the unconditional dynamics of this kind of two-way feed forward is exactly equivalent to this master equation. And now this gives us a really nice way of understanding why do master equations like this sometimes generate entanglement and sometimes they don't. So if I just have local operations in classical communication, I can never generate entanglement. So if I just had 2 qubits, if I deleted the qubit 2 over here, right, I could have Z1 plus IZ3. This process would never generate entanglement, right? Because I'm doing something locally here, locally driving this. That's classical communication. No entanglement possible. In this example, why can I get entanglement? Well, you're doing something non-local here, right, in this measurement. So in this example here, I'm not going to get entanglement between 1 plus 2 and 3. I could get entanglement, for example, between qubit 1 as my A system and qubit 2 plus 3 as the B system. Okay, so I've given you a bunch of ways of trying to understand the complex entries in this V matrix. There's this microscopic picture. It's related to broken time reversal symmetry. There's the overall consequence of the physics. It can generate entanglement. So that really, in my mind, defines a working definition of a quantum dephasing path. And then there's this really, really nice connection to continuous measurement and feed forward. Well, that lets us understand why it's not just any old complex V that can generate entanglement. You need a special structure. And so maybe I'll be a little bit quick on this, but so now the question is not all complex V's generate entanglement. If you come to me with some complex V, is it really a quantum bath? Will it generate entanglement? So the bad way of answering that question is you come to me with this V, I check all possible initial product states and see if I get entanglement, right? That's going to take a while. That's going to be difficult. There's a much smarter way of thinking about, can we generate entanglement? And that's using this, this notion of the partial transpose and sort of negativity. So if I want to understand, here's my collection of qubits, I partition them into A and B. Is there entanglement between A and B, even though the state of the system is not pure? I can construct this partial transpose density matrix, where I basically just do time reversal on the A qubits and not the B. That's a way of thinking about that operation. And then we know, this is the Perez-Horodecki condition, that this object here, this partial transpose density matrix, if it's unphysical, if it has a negative eigenvalue, then your original state was entangled. So why is this useful? I can now take our starting physical density matrix and construct a new pseudo, master equation that tells me how does the partial transpose evolve, right? So I'm trying to see can my dephasing dynamics entangle system A and B. I'm going to consider this object, right, and ask how it evolves. Okay, and it turns out the evolution of this partial transpose density matrix, it has exactly the same form as this equation, but a modified V matrix. Okay, and so now, can my original master equation generate entanglement? I take the original V matrix, which is necessarily positive. I construct this modified version, which tells me how the partial transpose evolves. If I get a negative eigenvalue, I basically know I can get entanglement. Okay, so the upshot of this is we can now really ask, does a given V matrix generate entanglement without having to do this kind of brute force check? And so just very quickly, what I want to sketch is, well, imagine we don't know if our system has time reversal symmetry, right? There's no reason to sort of say the bath has time reversal symmetry. How likely is it that we will actually get the bath generating entanglement, right? So again, we could sort of take the philosophy of what you might do in condensed matter when you're looking at a chaotic system or a completely random system. Let's just take the coupling between my qubits and the bath to basically be random, right? And let's ask for this full ensemble of like random baths for all members of that ensemble. How likely is it to actually get sort of entanglement generation? So that's what we did in this paper. We imagine this V matrix. It's built up of this W matrix. I have n different baths, n qubits. The W matrix tells me each qubit and each bath. We just take the real and imaginary parts of those coefficients to be Gaussian random variables, right, with zero mean and sort of unit variance. And so with this, and this is what people call the complex Ginebra ensemble, with this kind of random, dephasing dynamics where the V could be complex, it couldn't be complex, it might not be complex, we can now generate many, many random realizations of these baths for different numbers of qubits. That's what the n is over here. And the crucial thing to look at here is the y-axis, right? To test for entanglement, we're going to do this time reversal operation where the A system has one qubit, the B is all the rest of the qubits. We're going to ask if the dynamics can make that partial transpose density matrix become unphysical. Can it give it a negative eigenvalue? That's the harbinger of generating entanglement. And what we see is, as you go to more and more qubits, right? So here, this pink region is where we have, a negative eigenvalue. Statistically, with enough qubits, with this kind of very agnostic, completely random bath, statistically, you are almost always going to have the ability to generate entanglement. Okay, so the upshot of this is really the fact that complex entries in the V matrix could lead to entanglement. It's not some incredibly fine-tuned, delicate balancing. You need a V with a very, very special structure. If you just take a V that's big enough, you have enough qubits, and it's random, you're going to have this sort of entangling physics. Okay, so let me just maybe skip this for the interest of time. Not surprisingly, this has taken a little bit longer than I expected. This is the end of part one, and it's great. It's good to have questions. Zlatko, I will let you be the guide. I could probably give a taste of part two in like 5 minutes. This is also a good place to just stop if there's some immediate questions. So
maybe one immediate question, and then we can get a taste of part two.
Sure.
Can you help me or help us understand, let's say that I also had some kind of unitary ZZ interaction between the different sites. How would that fit into this model, or how do I think about that with this as well? We've had some coherent 2-qubit ZZ coupling.
Absolutely, right? So if we go back to even this kind of setup, if I had like just ZZ Hamiltonian interactions that were added here, well, the first thing is we know that can generate entanglement, right? So if I really have a Hamiltonian that lets my 2 qubits interact, there's no surprise that we could get entanglement. So generically, we would expect for some physical bath that would also generate some coherent ZZ interactions. The thing that we really focused on here was if you just look at the dissipative part alone, again, the naive thing would be, okay, if you get a Hamiltonian, sometimes people call this the Lamb shift Hamiltonian, right? The bath basically gives you a Hamiltonian, even if you don't want it, it mediates some interactions. We know that could generate some entanglement, right? But it's tempting to think that the purely dissipative part, right? So because there's no way to extract a Hamiltonian out of this master equation here, it's tempting to think that this is just noise, that this is equivalent, even if the V matrix is complex, to driving with classical noise. This by itself couldn't generate entanglement. And so the little, depending on your perspective, surprise is just the dissipative part of the evolution itself could generate entanglement. So does that help a little bit? So the Hamiltonian that would be there, that already could generate entanglement. The funny thing is just the dissipative part of the evolution, that on its own could actually generate entanglement. And maybe one of the things I'll say on that too is, in our paper, we basically go through an experimental protocol where it's kind of like a general set of sort of 1 and 2 qubit sort of Ramsey-style measurements, where you look at the phases that are acquired by 2 qubit superpositions like this, and you can actually distinguish the phases that you pick up in a superposition like this from just having an ordinary ZZ Hamiltonian interaction versus the funny kind of dissipative interaction that shows up here. So experimentally, and again, this is spelled out in great detail in our paper, there's a clear procedure to distinguish these 2 kinds of interactions. I don't know if that helps or not, Zlatko.
I see. Even if you have both going on with some.
Yeah, because there's a different, it goes back to that, what I call the dissipativizing interaction, right? The coherentizing interaction kind of has a symmetry between both qubits that are interacting. For the dissipative version that's coming from this master equation, there's a funny minus sign, right? Tells you it's not coming from a Hamiltonian. That has an experimental signature just in looking at how these 2 qubit superpositions actually acquire phases.
Yeah, I think, by the way, this is really cool. I didn't mention it earlier. I typed it in the chat, but the connection with the measurement feed forward is super duper cool. Is this also, can I think of this also as some lowest order non-Markovian noise bath approximation?
So, there is sort of, so lowest order in the sense that it's a Markovian approximation, right? So all of this is in the strict Markovian limit. This is completely a time local evolution. There's no explicit time dependence. But you're hinting at a really interesting question. All of this still goes through if we go to the non-Markovian limit. And that's also on our list of things to sort of understand more fully. Again, to us, this should just be a really, really boring master equation, right? This should have been like a warm-up project for a student. And it turned out even in the Markovian limit, there were some surprises lurking, some things that had not been fully understood. All of this gets more rich when you go to the non-Markovian limit.
I see, yeah, because I think of the non-Markovian as, the system, some information from the system goes to the bath.
Right.
The bath uses that to do something on the system, which is kind of what you have here. It's just, it's not coherent. It's a measure and feed forward. So that's why it looks to me a bit like that.
So Zlatko, that question does segue really nicely into the second part, really condensed to like 5 minutes.
Okay.
Which is exactly, if there's another question though about this part, I'm happy to do that first. Whatever.
There is a question from Laxmi, but let's take that at the very end.
Perfect.
And folks, feel free to post questions now, or if I missed your question, post it in the chat. Bring it back up as we come to the end after we let Ash here give us a taste of what's coming.
Great. And in terms of the taste, Zlatko, like 5 minutes, or should I do it even quicker?
5 is fine. 5, 7, it's okay.
5-ish. Perfect. So the second part of the story is exactly, again, what Zlatko was sort of hinting at. What about non-Markovian noise? And again, we like to build things up slowly. So we're going to think about non-Markovian noise, but we're going to think about it with just a single qubit, okay? And let's just start with classical non-Markovian noise. So what do I mean by that? Here is some classical real-valued noise. Its autocorrelation function is not a delta function, right? So if I look at the noise in time, there are correlations of the noise at different time. If it starts high, it's going to stay high for a little while, etc., right? The spectral density is not a constant. Even in the classical limit, if I drive my qubit with this, let's even take it to be Gaussian, classical, colored noise. If I also add a drive on the qubit, so in this case, like a Rabi drive in the rotating frame, this is not a trivial problem, right? Even though this is Gaussian noise, you think, oh, I can say everything I want about this. The fact that these things don't commute, there's actually something here that is non-trivial to understand, right? And naively, the standard ways of thinking about a non-Markovian noise problem is, well, look, there's some memory. This autocorrelation function is extended in time, right? The noise is correlated at different times. if I want to know how the density matrix evolves at time t, damn it, I have to know what it was doing at earlier times, right? And there's some integral differential equation that Q-tip will not, help you with, right? This seems really, really bad. So we want a useful modeling tool. What's a simpler way of trying to think about this? So a, seemingly attractive approximation is to say, well, look, here's my driven qubit. I have this sort of classical dephasing noise that's non-Markovian. If I didn't have the drive, I can solve that exactly, because then there's not this problem of things not commuting with itself, right? In that case, I know I can describe the dephasing from this Gaussian noise, even if it has a colored spectrum. So for example, if this was like 1 over f noise, you might expect in some regime the dephasing you get is an exponential not of t, but of t squared, right? To a good approximation. So you could say, well, how do I get dephasing that's like e to the minus t squared? Well, it's sort of like having a dephasing rate that's growing with time, right? So if I didn't have any driving of the qubit, I could mimic the exact answer by writing down a master equation that's nice and local in time, right? There's no integrals here. I just put in a time-dependent dephasing rate. Okay, and this is sort of like cheating. Like you know what the answer is by doing things properly. You reconstruct it in another way. And now the tricky thing is, like that's all fine and well if you don't have the driving. The H naught is this. Now you put back in the driving. And then you have a problem, right? So this is a very nice equation to look at, right? Because it's still time local. It gets the correct answer if you don't Rabi drive the qubit at all. The problem is as soon as you put the drive in there, this is sort of an uncontrolled approximation, or at best it's valid to 0th order in the driving. And so the kind of motivation for our work is there's still something very nice about this, right? Replacing the non-Markovian noise by like a time-dependent dephasing rate. But can we do this in a more systematic way, in a way that keeps the interplay between the driving and the noise? And one way of thinking about this is it's like a poor man's way of deriving a time convolutionless master equation. Okay, so the upshot is, and again, because time is limited, there's a systematic way of, for this problem or other problems, deriving the kind of master equation we want. Something that almost looks like this, time-dependent rates. But now you can do it in a way where you sort of know exactly what is the nature of the approximation. You're keeping the fact that the driving and the noise interplay with one another. And just to give you a sense of the answer, even in this problem where you just have noise driving your system on a single axis, the effective description you get, it actually has 2 independent dephasing processes, right? And these are like Hermitian operators. So the axis of those 2 dephasing processes is changing in time. They have rates that are time dependent. You even get a renormalization of your qubit Hamiltonian that is time dependent. And even crazier, the rates, right, are time dependent. One of them is negative, right? And despite all of that, right, this description, which is fully time local, gives you a real improvement in accuracy over this simplistic approach. And maybe I'll just end with this. Let me just show you results for modeling 1 over f noise, right? In this problem of just a simple Rabi-driven qubit. So this is showing the fact that you have positive and negative effective dephasing rates, which seems really worrying. If you really stare at the screen, there are some black lines here, right? The black lines are coming from a kind of numerically exact calculation, right? And it's also giving you these negative rates. So these negative rates are real. They're part of the true exact sort of evolution map, and we're capturing that. And this here is a measure of approximation error. How close is our approximate, nice to look at master equation to the true evolution? Our method is this blue curve here. That naive 0th order method, which has been used in a number of different papers, is this orange dashed line here. You see that sort of in regimes that are kind of interest for, let's say, doing a gate, you have more than an order of magnitude improvement in the accuracy. So just to summarize the second part of the talk, there's a really nice way of rigorously taking a non-Markovian noise problem, making it into something that almost looks like a time-local Lindblad master equation. But there's some interesting surprises here. even one noise process gives you multiple dephasing processes. Those processes can have negative rates. So let me flash up my conclusions here. I've told you hopefully a flavor of both of these stories. Hopefully convince you that studying correlated noise, it's not just important, right, for making progress in these quantum technologies. There's also a lot of just really interesting physics here. So with that, I will stop. And yeah, I'm happy to stay on for whatever time we have to answer questions.
Thank you, Ash. Congratulations on the absolutely beautiful results and deep insights. Quick question from Laxmi. It's from a little bit ago. Doesn't the Perez-Horodecki criterion, isn't that valid for 2x2 and 2x3 systems? What about higher dimensions?
Yeah, so let's go back to this, right? So yeah, so we're using this Perez-Horodecki condition that if I do this partial transpose and I end up with an unphysical density matrix, then I know I have entanglement. And that's what I'm sort of detecting here, right? So now, for example, all of these guys here where I didn't get this eigenvalue that was less than 0, right? I can't say for sure that the dynamics there doesn't generate some form of bound entanglement, right? So in the more general case with many, many qubits, if I get a negative eigenvalue, right, so in this pink region here, we know the dynamics is entangling. If I don't get that negative eigenvalue, then yeah, in the general case, it's possible we could still have some entanglement generation there. And we haven't really kind of looked into whether, there are regimes where you kind of get that bound entanglement.
Okay, great. Thank you, Ash. I have some questions on the second half of your talk. So the first one is, maybe you can help me remember this, but if I think of, for instance, in superconducting qubits, we oftentimes have this 1/f noise. If I think of that, usually the T2 decays in a Gaussian profile, which kind of reminds me of this. And you're saying that I should be very careful with how I think about that, because I'll get this, like that model that you wrote here, it's not a great model for that. And you'll get some weird other effects that we don't usually think about.
Yeah, so I think the crucial thing is, like, if I didn't have any driving on the qubit at all, I was just doing like a free induction decay experiment. And I really think the 1/f noise is this kind of classical Gaussian 1/f noise. So then this argument that I'm going to get something like this kind of Gaussian dephasing, that's perfectly rigorous. The argument that this master equation without this stuff would also give me that, by construction, that's true, right? So it's almost saying, if it's just dephasing dynamics, pure dephasing dynamics, you know the exact answer. I can reverse engineer a simple master equation with this time-dependent rate that gives me that. All of that is fine. Where things get problematic is if you now say, oh, I'm actually doing a gate. I'm going to be driving my qubit. I'm going to turn on some fields. I want to understand the fidelity of that gate in the presence of this dephasing noise. I'm going to model that dephasing noise using this same gamma phi of t. That's when you have a problem. This gamma phi of t, it's been cooked up to give you the correct answer. What does the noise do if you don't drive the qubit? Once you drive the qubit, what our theory is basically saying is that you really need to modify the form of this effective time-dependent dephasing rate. And a really physical way of saying it is, whether you like it or not, you're going to end up doing some continuous dynamical decoupling, right, when you start driving your qubit, right? And when you do that, that is going to actually affect the way the noise messes up the state of the qubit. And that's actually one of the things we're sort of excited about. Again, it's ideas that people have thought about in the past, but you could imagine revisiting. Now knowing that when you drive the qubit, it affects the form of these dephasing rates, it affects the non-unitary evolution coming from the noise. You could imagine when you're optimizing your gate, you could really try to, in a sense, have some inbuilt sort of dynamical decoupling, right? So there's, earlier work on these ideas, again, from people like Lorenza. This gives another interesting way to sort of try to engineer that kind of happy situation.
One other situation that this reminds me of, where you see effective negative decay rates on like T2 is when you couple the qubit to the readout cavity and you do this Polaron transform and you derive an effective stochastic master equation for the qubit with its coupling to the cavity, you can get this negative damping rate because information in the cavity can leak back into the qubit in the regime that chi is larger than kappa. I wonder if,
Yeah, I think it's a generic feature of non-Markovian evolution. When you do this trick and you say, I have some non-Markovian evolution and I want to try to represent it with some time local dynamics, right? So this is saying like, look, if I have some non-Markovian evolution, there is some map, right? Some channel that describes the dissipative evolution. I could always try to construct some time-dependent local generator by just comparing the map at time t and the map at time t plus dt. So physically, this is saying I have some non-Markovian evolution. I'm going to insist on looking at it as some time-dependent Markovian process. And then this idea that information goes into the bath and comes back, in a way, the only way to get that is to have these sort of negative rates. So I think, yeah, you've phrased it really nicely. The existence of these negative rates means, on some level, you're undoing some of the dephasing that might have happened at earlier times.
All right, thank you, Ash. And the final question, I'm not sure this is really a question for you, but I'll just bring it up. If we're learning and interacting with qubits via Qiskit, is there some kind of measure at which we know to worry about these more complex noise scenarios? And
it's a really interesting yeah, so even with these kind of really nice sort of test beds that we now have available, some of these basic protocols we have to like, let's just be agnostic. Do these funny kind of noise correlations exist, right? There is a definite experiment you could sort of do in seeing how different superpositions pick up phases. You could try to do this kind of correlated noise spectroscopy. And that's an interesting, I think there's a whole bunch of other wrinkles that you have to think about when you do this in a more realistic setting. But I think it's a really interesting idea to like test this, right, in some setup and see, like, be agnostic. Don't start out by saying, oh, I think this should be here, or it shouldn't be here. This is something that quantum mechanics allows. Unless I'm sure there's no broken time reversal symmetry, this could be part of the physics. Let's let the experiment tell us if it's there or not, right? So that would be a fascinating thing to do, yeah.
I agree, that sounds very interesting. I think with that, seeing as we're 15 minutes over, Ash, if you'd like to say any final words before we close out.
No, just to thank you again and to thank the audience. Yeah, it was fun to get a chance to talk about this work, so yeah.
Yeah, once again, thank you for accepting the invitation. Congratulations on the really nice results to you, the team. We'll point out Ali Reza in particular here, since our newfound connection. And folks, with that, I'd like to thank you for tuning in. This talk will stay recorded, so you can go back and rewatch it to know what's coming up next week. Subscribe to the Qiskit YouTube channel. And Ash, on behalf of myself and everybody who tuned in today, and you can see some comments saying great lecture and great talk. I'd like to thank you very much for coming, and we'd love to have you back sometime.
Great, thank you very much. Yeah.
All right, folks, have a great day. See you next week.